Hello, everyone. Welcome back to CP 517-WS, Digital and Computer System Architecture. This is part 4 of lecture 10. We're going to talk about snooping protocol. As we mentioned earlier, we have two protocols. One is directory-based, one is snooping-based. Snooping-based is similar as common data bus-based communication. Directory-based is more like centralized management. So we're going to go to the common data bus similar one first, snooping-based protocol. Snooping, right, or Snoopy based cache coherence protocol means everybody's snooping is detecting on the common data bus, like a switch. If a relevant transaction is happening right now, then we're going to take actions to either invalidate, update, or supply the values. It depends upon the state of the block and the protocol, right? For instance, let's see. In this example, if we have processor 3 here, processor 3 is here. It's like a drama, right? So the drama contains a couple of players. Let's say we have the triangle baby, square baby, and the circle baby. So the circle one is sending a request saying, I want to invalidate at the event 4. Sorry, event 3. The circle one, like processor 3, want to send invalidate of U on the bus. Okay, it sends invalidate on the bus. So what we're going to do is processor 3 and processor 1 is both of them are snooping on the data bus, and they figure out, oh, okay, this is invalidated U. So when processor 2 see U, okay, its own cache, there's no U there. Then processor 1 see, oh, there's a U here, and I do have a U cached, so I will change invalidate the U equals to 5 in my cache line. And then what's gonna happen is step 3, that is setting U equals to 7. So basically we first invalidate and then we update, right? It changes, then this goes to the MOSI or messy, right? So it has to change the status of the block as well. Okay, the architecture building blocks that are required to support the snooping protocol is the cache block state transition diagram. It's a finite state machine specifying how disposition of block changes from invalid, valid, dirty, shared, etc. And they use the broadcast media to broadcast the transactions, and this media is atomic. So whoever wants to use this media, only one of them can use it. So basically, there cannot be both processor 1 and processor 2 are sending some data on the bus. So it's exclusive, and only one can have the data bus. This is a fundamental system design, but physically, you definitely have more complications to support that. Basically, logically, we have a single wire set of wire connecting several devices. So that single wire can only allow one bit to pass or one information to pass. The protocol are like arbitration, command, address, and data. So you first arbiter, say who's gonna get it, and then you find a command, send a command, and with the address and data you want to pass. Every device, including processor 1, processor 2, processor 3, and probably the memory, they're gonna observe every transaction on the broadcast media. Broadcast medium enforces serialization of read or write accesses, write serialization. The first processor to get media invalidates others' copies. Implies cannot complete write until it obtains the bus. All coherent schemes require serialized access to the same cache block, right? So it's like for the same cache block, what happens is the bus, who get a bus first? Who get it first, right? So it's like the bus is the single unique timer who get it and what order, and then the update of the results gonna be also showing that specific order. We also need to use that bus to update the block as well as finding the up-to-date copy of the cache block, like in write back case. Okay. Locating the up-to-date copy of the data, there are two ways. First is a write through to do a little bit of review. If you have a cache here, and then you have the memory. In write through, whenever you update the cache, you also update the memory, okay? That's how you go through the cache. In write back, sorry, this is a write through. Sorry, it's RWT, right? It's not WP. In write back, it's like whatever update you have in the cache, it's kept in the cache until you have to write it back to memory. Okay, like if I first write to the cache and later I read it from the cache and then update the cache again, so it's always owned by this cache, right? That's what we say by MOSI, right? So it's owned by this cache. So you don't have to write it back to the memory until you find other caches want to have this data. So you probably have to write it back to the cache. So you can see that most of the recent copies in write through, it's always synchronized, consistent between cache and memory. In write back, it's typically not consistent, like only the cache holds the up-to-date copy, right? Both of them can use a snooping mechanism, snoop every address placed on the bus. If the processor has dirty copy of the request cache block, it provides in response to a read request and aborts the memory access. Okay, if it is not write back, then you can get it from the memory. The complexity from retrieving cache block from a processor cache, which can take longer than retrieving it from memory, that's true, right? Because you probably have to change the status of the cache block, and also you have to do tag comparison. You also have to go through the inter-process communication because it could be remote, right? Another cache. Probably it's easier even you go to the local memory. However, write back needs lower memory bandwidth because whenever you are updating on the same local cache, you don't have to push it down to the memory, right? Most recent multiprocessors uses write back. They support large number of faster processors. That's actually pretty straightforward. Cache resources for write back snooping. Normal cache tags can be used for snooping. The valid bit per block makes invalidation easier, right? We can use a single, just set that bit or not setting that bit. Read misses is easy. Are easy since they rely on snooping, right? Right, we need to know whether any other copies of the block are cached. If no other copies, no need to place a write on the bus for write back. For other copies, if they do, then need to place invalidate on the bus so that other copies can be invalidated. They know that this is not up-to-date results. Okay. So to track whether a cache block is shared, we add an extra state bit associated with each cache block, like a valid bit or dirty bit. When write to shared block, we need to place invalidate on the bus and mark cache blocks as private. And then further on, there's no further invalidation will be sent for that specific block. This processor will be called the owner of the cache block. Owner then changes states from shared to unshared or exclusive. The cache behavior in response to the bus, right? So that's what we mentioned by here. So on one hand is the active behavior, right? Like the circle baby is sending something, sending invalidation to the bus. And then if you get rid of this, okay, you don't say anything here, you only focus on this process, then this process is always snooping on the bus, because this guy is not the one who's sending the signal, it's the one who is detecting whether other guy is sending the signal. For this one, it will detect the updates or the signals from the bus. Okay. Must check the cache tag addresses, and this could potentially interfere with the cache process access, right? So the snooping, the coherence protocol checks the tag and address. Similarly, the typical memory access also has to do that, right? A way to reduce this kind of interference is to duplicate the tags, which we're going to talk about next lecture in detail. So basically, we have the same tag. One is for accessing, right? So when CPU is really just accessing the data and say if whether this is the data of your interest, you do the comparison of the tag, the invalidate, and the data, right? If you remember, you use the index to figure out the cache block. And then use a tag to compare whether this is the data of your interest. And then use the invalidate to see whether the value is invalidated. And then this is the data entry, if you remember, right? We're going to talk about this in detail next lecture. Another way to reduce interference is use the L2 tag. The reason is because L2 is less heavily used, because typically the heat goes to L1. L2 is relatively, I would say, not that busy. And also L2 is inclusive. So whatever is inside L1 typically should be inside L2. It's called inclusion property. If Snoop gets a hit in L2 cache, then it must arbitrate for L1. So this helps us to filter out those unnecessary checks to L1, right? So only after you have the L2, have this tag in L2, it means it's potentially in L1. Then we go to L1 to check again, right? This typically requires to stall the processor, okay? So taking all of them together, this tells you two kinds of cache protocols. One's write through, one's write back. And then it tells you how the snooping data structure protocol works. You can think of it as an active participant, right? So who's like the processor 3 for event 3. Or you can think you are a passive, okay, a passive participant. It's like your processor 1 and processor 2. So for passive guys, they probably have to snoop on the bus. For the active ones, they send the information to the bus, right? Well, whoever grabbed the bus can be the active one to send the information, and others who didn't get it, so have to listen, right? Well, on the other hand, maybe at the next iteration, like the event 4, processor 1 gonna be the one who grabbed the bus. They're gonna send, okay, I have a read miss because why? Because my U is already invalidated, so I'm gonna read miss on the bus. And then at this moment, P2 and P3, especially P3, where it was an active participant, right now becomes a passive one because it's gonna detect, hey, there's a read miss on you. So I'm gonna have to change my status and provide a data of u equals to 7 to processor 1, right? And probably also write it back to memory. Okay. So taking all of them together, this is a feeling about how snooping works. It's very similar to common data bus. You have a bus here. This bus is atomic, okay? What this is different from common data bus is common data bus, it allows multiple traffic on the common data bus in Tomasulo's algorithm. In this case, in snooping, it's an exclusive resource. Only one can grab it. Once you grab it, you can use it to communicate with other people. So you need an arbiter to do that, right? Okay, this is part 4.